Hello and welcome back, everyone. Let's quickly get started with the third lecture of the series. Before I hand the mic over to Nils, a quick announcement for the online participants. If you have questions, please raise your hand and form a queue. We'll unmute as and when we get time to ask those questions.
So let me start again by a very brief recap of what we did yesterday. So we started out with the Klein-Gordon equation and found a way to handle this second order PDE by using this ansatz. That's basically just a product of something that depends on R, something that depends on the polar angle, and then some harmonic time and azimuthal dependence. And making this ansatz, we were then able to separate this PDE into two second order ODEs. That's two ODEs, one for R and one for S. And at this point, we haven't really made any approximation. We kind of just rewrote the Klein-Gordon equation, and we made the assumption that the solution looks something like this. But then to actually solve these two ODEs, we then assumed further that this, this quote-unquote gravitational fine structure constant alpha, which is just mu times m, is much smaller than 1. And in that limit, we were able to obtain a solution which was basically just the hydrogen atom. And then going a bit further, we then realized that actually the hydrogen atom isn't quite right because it doesn't satisfy the correct boundary conditions at the horizon. And when we include this additional fact that the boundary conditions at the horizon are ingoing boundary conditions, then we realized that the frequency omega was actually complex. And so it was then split into a real part plus some imaginary part, where the imaginary part then controls the exponential decay or growth of any given mode. And then I kind of just motivated the actual calculation, assuming that omega is actually complex instead of just real for the hydrogen atom. But doing this calculation, we then wrote down an expression for omega I. And this expression basically told us that omega I is positive in some regime, which implies that the field phi grows exponentially in time. And it grows exponentially time exactly when the superradiance condition is satisfied, which is this condition. Okay. So then I wrote down this very lengthy expression for the growth rate omega I. And I want to write down at least a shortened version of this again, because there's a lot that we can learn from just analyzing that expression a little more. So far, the only thing we did was look basically at the overall sign of omega I to see when it's positive and when it's negative, to find out where the unstable regime is. But we can learn more from that. So let me just kind of copy what I wrote on the board yesterday. And let me not write down all the things. So here C sub L n hat is basically just this function that was a bunch of factorials depending on the index L and the Overtone number n hat. So I'm not going to write this out again because it would just take a while. And then the last term was something like this. Where this chi is just the dimensionless spin, so A over M. Okay. Okay, so the first thing I want to do is kind of in the spirit of looking at solutions for small alpha, I want to write down an expression, or I want to simplify this expression in this particular limit, where alpha is very small, okay? So let's assume that alpha is very small. And so basically what happens then is that this term at the back here, so mu times r plus. So r plus is basically order m, because it's just, you know, m plus root m squared minus a squared. And so basically you get a, roughly speaking, you get a factor of alpha here. And so this second term is suppressed compared to the first term because the first term is 0th order in alpha. And so we just keep the first term. Okay. And then secondly, I'm interested in just m equals 1 for now, because as we will see in just a moment, this will be one of, or the most important cloud configuration. So if m equals 1, then we have a chi-squared here, we have a minus chi-squared here. J is only 1 because I should also say that L is equal to 1 here. Then L is equal to 1, and so all of this term is equal to 1 plus order alpha things. Assuming this, okay? Right. So then this first term just gives us the overall power in alpha. And then what about the second term here? So let me write this out. So we have omega r minus m omega h, where m omega h is just a over 2m r plus. And then we have this 2 r plus here, okay? Now again, this r plus, as I said over here, is just order m. And an omega r to leading order in alpha is just mu. So again, this just gives us an additional power in alpha that we don't really care about. So the only thing we have to worry about is the second term. And so the second term is basically just, So the second term is basically just the dimensional spin a over m times the mode number m over 2, and then we multiply this by 2 here, and so we get m chi. And so then we need to work out what this number is, and then you just, I wrote on the formula yesterday, you just plug in the numbers, and basically what you get ultimately is that omega I is equal to, so L is equal to 1, so this is alpha to the 9, alpha to the 9. Then we set m to 1, so this is just chi. And then the number that pops out of here is 96. And so this is then plus order alpha to the 10. Okay? So basically what we learned from this is that at small alpha, the growth rate just kind of has this power law dependence on alpha and goes linearly in the spin. So omega r, right, so we learned yesterday that omega r is equal to mu 1 minus things alpha squared. So basically at leading order it's just mu. And then you have a mu times r plus is order m, and then it's subleading in alpha. Right, so now what happens, so now we looked at alpha very small, but what happens for alpha order 1? Now I should stress that this expression we obtained, of course, in this limit where alpha is very small. So technically speaking, we can't apply this there. But as you can confirm numerically, at least to a certain degree, this is still valid, even for alpha order 1. And there's one qualitative feature in this equation that is very important that will definitely show up in any kind of numerical calculation you do that is more correct for alpha order 1 too. And the important contribution here that is relevant for alpha order 1 is this term. Okay, so to understand what this term does, let's consider a nearly extremal black hole. So for a nearly extremal black hole, so I'm just going to write this as a roughly approximately m, but of course implicitly assuming it's smaller than m. So for this, the horizon frequency, omega h, which again is just this expression. So here I'm going to replace the a just by the m. Okay. Then the r plus for a nearly extremal black hole is again just m. And so we end up with 2 over m squared, or 1 over 2m. And so what we can do to understand this term now is to pull out the m from this r plus. Okay, so I can combine this. What we learned from this is r plus times omega r minus m over h. This is basically, again, r plus for, nearly extremal black hole is basically just m. So then this is approximately m mu minus m times 1/2. Okay, so the 1/2 comes from the fact that this is 1 over 2m, and then the m gets canceled from the m in the r plus, and so we end up with a lowercase m over 2. Okay. And so now the question is, okay, what happens if we go towards large alpha? And so what happens is that basically at some point this expression, so for small alpha, this is negative, but at some point it will be 0. And it will be 0 exactly when alpha is approximately, by approximate I just mean that we are in the nearly extremal case, not in the extremal case. So maybe like this again like this, m over 2. Okay, so mu times m is just alpha, and yeah. So at this, when this is basically just satisfying that this is equal to m over h. Okay. So basically, whenever alpha is, at least in the extremal case, roughly m over 2, then this term will be 0, and therefore the growth, the superradiance rates go to 0. Okay? So let me plot this. So here I'm going to plot just log omega I m, and then this is alpha. Well, so basically this is just equivalent to alpha minus m over 2, right? Equal to whatever, r plus omega r minus m omega h. And then you just set this to 0. And so the smaller just comes from the fact that here I kind of looked at the most extreme example where we are on the extremal limit. And any spin below that, alpha, the condition where omega r equals m omega h is satisfied at a lower alpha than this. So this is kind of the upper bound for each m mode. Okay, so let's plot this. And let's focus first on the m equals L equals 1 mode. Okay, so this is 0 here. And so for small alpha, we derive this expression. So it's basically just, if we set chi to 1, again in the most extreme case, or approximately 1, then it's just some alpha to the 9 scaling. So in a log plot, this will look something like this. Okay, so here, this corresponds to an alpha to the 9 scaling. But then we also know that at 1/2, now I'm setting m to 1, we know that the superradiance rates again go to 0. Okay? And so in between, you would then have to use the entire complete formula to get what is in between. But basically what happens is you have to go to a maximum somewhere. and then it has to drop. So for small alpha, the superradiance rates, or equivalently timescales over which the cloud grows exponentially, for small alpha, these timescales are very long. So it takes a very long time to grow these clouds. Then for intermediate alpha, let's say, I don't know, 0.3 or something, there's a peak. And so this is kind of maximizing the growth. So it's as fast as it possibly can be. And then there's this critical alpha, where the superradiance condition is quote unquote saturated, meaning that your omega r is equal to m omega h. And there, superradiance shuts off, and again, the sign switches from positive to negative, and therefore there's no longer a growing. Now this, of course, was basically for chi equals 0.9999, and so on. It's kind of the most extreme case. But in general, the omega h will depend on spin, and therefore the saturation will also depend on spin. And as I was saying, this is kind of the upper bound. So any smaller spin than basically extremo means that the saturation happens at smaller alpha. Okay? But the scaling at alpha roughly equal to 0 is basically just an order 1 number on the spin. And so basically, at small alpha, these lines are basically on top of each other for different spins. But then at larger alpha, they kind of differ and then go down. So this, could be chi 0.99, and then you get a different line for chi 0.9, and then yet another line for chi 0.7, and so on and so forth. And so at 0 spin, obviously, this is just 0 at small alpha. Okay, so now we've learned that, okay, at least for the m equals L equals 1 mode, it is advantageous, or at least the growth of the superradiance state is fastest if the spin is largest. And also the parameter space over which the black hole is unstable to the superradiance growth is also largest. But now what happens for a different set of modes? So here I assumed m equals L equals 1, and implicitly I also assumed that the overtone number is 0. Okay? But we know that omega r depends on the overtone number, and we also know that these C, L, and hats depend on the overtone number. So basically what this does is it will just change the overall factor in front. So it won't change the overall scaling, but it will change the number here. And in fact, it will make the denominator larger. So higher overtones lead to a smaller number here, and therefore slower growth. Okay, so if I say this line is n hat equal to 0, then the n hat equal to 1 has the same alpha scaling, but just slightly different value. Okay, so it just grows not as quickly. And then, and this is kind of a bit more difficult to see, this superradiance condition also depends on the n hat, because omega r depends on the n hat, as I wrote down yesterday. And so where this line goes through 0, again, is no longer 1/2. It's something smaller than 1/2 for the same spin. So it will look something like this. And so any other higher overtone than 1, let's say 2, 3, 4, these are kind of stacked all below here. So you have like a n equals 2, then you have an n equals 3, and so on and so forth. It just becomes successively slower rates. So now I'm going to draw the exact same plot again, but now focusing on not just the m equals L equals 1, but higher numbers. So m equals 2, 3, 4, and so on. Okay, so again, we're going to look at log omega I m versus alpha. And so we have 0, 1/2, 1, 3/2, 2, and so on and so forth. And so now we're interested in the m equals L modes. So the m equals L modes, as you can see, the larger the L, the higher this power in alpha. And so the smaller the number will be, at least at small alpha, right? So for m equals 1, it was alpha to the 9. For L equals 2, it will be alpha to the 13, and so on and so forth. And so we already know that for small alpha, you know, the m equals 1 mode looks something like this. And for now, I'm just going to assume that the spin is 0.999 and so on. But then we know that the scaling, at least at small alpha for the higher m's, so this is m equals L equals 1, is slower. And therefore, the slope here is not as steep. And so then it will look something like this. So this is the m equals L equals 2. And then similarly, this is the m equals L equals 3. And so on and so forth. Right, so L can be 0, that's right. But L equals 0 also means m equals 0. And for m equals 0, this is just negative. It will always decay. So the only states that can be superradially unstable, based on the condition here, are the ones that have m larger than 1, larger than or equal to 1. So this is kind of the general structure for these different modes, and it kind of just gives you a visual representation of what this looks like. Okay, now I want to briefly mention what happens if we're not just interested. So this is all for a scalar field. But what happens for a vector field? I just want to briefly mention the slight differences here. So what I mean by vector field, let me just very briefly write out what I mean by a vector field without doing any of the calculations. So basically what I'm doing here is I'm just changing the Lagrangian of the theory that we wrote down on Monday. And instead of having a scalar field, we now have a vector field. And so if you ignore this term, then this term is just the regular Maxwell equations, right? So if you vary this term with respect to A, which is the vector potential, then you just get the regular Maxwell equations. But now we have this additional mass here. And that's basically the exact same term as for the scalar fields, but now just for a vector field, okay? So in theory, or in principle, what you'd have to do now is you'd have to get the equations of motion for this, and then do the exact same calculation that we did for the scalar field. And the only real technical difference will be that there's just more indices, okay? So basically, the equations of motion that you get here is this, okay? Under the assumption that, and so really the only thing you did was replace the phi by an A alpha. But now, because you have an alpha here, this is actually 4 equations. And so instead of solving a single equation, you now need to solve 4 different equations plus this additional constraint. And so it just becomes, on a technical level, more complicated. But the methods you use are basically identical to what we did for the scalar field. So I don't want to go through that, but I want to tell you, I want to give you basically the final answer for the growth rates, because that's the biggest difference. So the growth rates for the vector look something like this. Okay, so here the MV is just the azimuthal index. So let me write this as azimuthal index. So basically the same as in the scalar. Then we have this S. So this S basically just indicates the different polarization states you can have. So it just takes on the values -1, 0, or 1. And then really the only difference is that we have some different numbers. So here I wrote it as G, which depends on all these indices. And G is basically equivalent to this C that I wrote down here, just that the numbers are slightly different. Okay? But crucially, you can tell already from this that the leading scaling in alpha, so if I again expand this for small alpha, so again assume alpha much smaller than 1, then you can see that this will be alpha to the 7 for MV equals to 1 and S equal to -1. Okay. So, and then of course there are a bunch of numerical values here plus the spin dependence, but the spin dependence is basically the same as in the scalar case, and then the numerical values are slightly different. But crucially, the power here is alpha to the 7 as opposed to alpha to the 9 over here. And this already indicates to you that in the case of the vector, the growth rates are just much, much faster. And as it will turn out, if you do the full calculation, the growth rates of the vector can be several orders of magnitude faster than those for the scalars, which will then have obviously observational impacts the way you look for the presence of these clouds using gravitational waves. I see, right. So, right, so I guess you're interested in why we didn't consider those? Those are basically, they're slower growing. And you can see this, how can you see this? So this will, right, so these will basically saturate earlier for smaller alpha. And they also enter here, and so the smaller the m, the smaller this number compared to the maximum m. So basically that means that they're just subdominant. By subdominant, I mean the growth rates are smaller compared to the maximal case. Okay. Right. So basically, alpha is equal to mu m, and mu is equal to m c over h bar. Okay, where let's call it mb, the boson mass. Okay. So the assumption really is that, well, we don't know because we're trying to use this mechanism to look for a boson of a particular mass. We don't know this number, but we assume that in the universe there won't be a multitude of these bosons, and if there is, you can then kind of disentangle it still. But the assumption is that this MB is kind of fixed. In the Lagrangian of the standard model, or the extension to the standard model, it would just be a fixed number. But the M, the black hole mass, is of course not. So different black holes will sit at different locations along this alpha axis, okay? Even at fixed boson mass. And so you kind of need to understand the whole alpha regime to be able to tell what's going to happen if a boson mass that has some MB exists in the universe, because then different black holes will behave differently because they sit at different locations here. The growth rate will be different, the evolution will be different. For values below 1, it's going to be smaller. The slope should be 13, yes, but but for values below 1, the numbers with the higher powers are going to be smaller. Well, right. So this is just a way to get a dimensionless number, and you'll see in the tutorial today different, yeah, as you say, different black hole masses will have different growth rates, even if alpha is fixed, right? So basically, I'm just factoring out the black hole mass dependence from the growth rate. But yeah, you're right. Even though different black hole masses will sit at different locations here, the growth rate will still depend on the black hole's mass. But you'll see that in the tutorial today. Okay, so now we kind of understand where in the parameter space there is an instability to start with, which is basically when there is a mode that satisfies the superradiance condition. And we also kind of understand which mode satisfies the superradiance condition, where in the parameter space. And we also roughly understand which of the modes is the most unstable one. So the most unstable ones are, of course, the ones with the largest spinning black hole, but then also the smallest m equals L, and the 0th overtone, basically. Okay? But now the question is, okay, we know we can, using this machinery, we can then figure out how quickly the scalar field, or equivalent to the vector field, will grow in time. But as was pointed out yesterday and the day before yesterday, this growth can't, go on indefinitely. And so what are the nonlinear effects that will basically stop the growth of the superradiance cloud? Okay, and to understand this, we have to go back to what you derived in the very first tutorial, and that's basically the available rotational energy of a black hole. So for a near extremal black hole, this is, these 29%. Let me write like this. The rotational energy of the black hole, roughly 30% of that, 30% of a near extremal black hole is rotational energy. And in principle, that can be extracted from the black hole, okay? So in principle, because this process extracts this rotational energy from the black hole, it can only go on until these 29% are kind of spent and extracted into the cloud that then sits around the black hole, right? So how can we understand this process in which it extracts the energy and then the growth stops a bit more quantitatively? Okay. So basically what you will show in the tutorial today is the following. You show that the flux of the scalar field across the horizon, so that's basically, how much of the scalar field energy goes into the black hole or comes out of the black hole, for a given state that kind of looks like this. So basically assuming the scalar field has this particular form, you can then write down the following equation to figure out what the flux of energy through the horizon is. And it basically looks something like this. Okay. Where this d squared depends on the exact value of the scalar fields on the horizon. But this isn't actually too important because the flux of angular momentum through the horizon, so basically that is the same idea. You have some cloud state that can extract or accrete angular momentum onto the black hole. The flux of angular momentum through the horizon takes basically the exact same form. And so what you can see is that the energy flux is negative if we are in the superradiance regime. And basically the way I define this is that if the energy flux is positive, energy enters the black hole. And if the energy flux is negative, then it extracts energy from the black hole, okay? And exactly extracts these up to 29% of rotational energy that is contained in the Kerr black hole, okay? And then similarly for the angular momentum flux. You extract some angular momentum from the black hole when the superradiance condition is satisfied. No, it's just, it's some integral over the value of the scalar field at the horizon. Yeah, you'll see this in detail in the tutorial today, I think. Yeah. Okay. And so one neat relation we can get from this is the following. So the flux of scalar field energy entering the horizon and the flux of angular momentum in the scalar field entering the horizon is basically just the ratio of the real part of the frequency divided by the mode number m. Okay, because all of this just cancels. Okay? Or equivalently, we can just write this as dE by dJ. So what happens intuitively here? While the superradiance cloud grows, this is negative, and therefore there's a negative flux of energy across the horizon. So the scalar field configuration extracts energy from the black hole. At the same time, it extracts angular momentum as well. So while it's happily growing, it reduces the spin of the black hole at the same time. Okay? And so what happens when the spin is reduced, we know that the horizon frequency is proportional to the spin, A. And so as the superradiance instability extracts angular momentum from the black hole, the horizon frequency of the black hole reduces. Okay? So basically, if the spin were to go to 0, then the horizon frequency is exactly 0. Okay? What does this mean for the instability? Basically, it means that, let's imagine we are here in the parameter space. Okay? So here, we have some growth rate to start with. And so the superradiance cloud starts growing, and then extracts energy and angular momentum from the black hole. Now, what this leads to is that this omega h starts to decrease over time. Okay? And therefore, the line where the superradiance rate goes to 0 also reduces. Okay? It kind of shifts towards smaller alpha. Okay? And at some point, we'll be in the situation where it exactly matches the location where we are in this diagram. Okay? So at that point, we then expect that the superradiance rate goes to 0 and the growth shuts off. Okay? So how can we formalize this a bit? So the mass, the final mass of the black hole, MF, is basically the initial mass of the black hole minus MC, where MC is the mass of the cloud. Okay? So we just basically deposited some rotational energy in the mass of the cloud that is now no longer inside the black hole. Okay? And then similarly, for the final spin, we have some initial, for the final angular momentum, we have some initial angular momentum, and then we have some JC, which is basically the angular momentum contained in the cloud. Okay? But now, just now, we derived this neat relation, or I basically told you that this neat relation exists, and you're going to derive it in the tutorial, that the change in energy versus the change in angular momentum extracted from the black hole has this particular ratio. Okay? So we already know that if MC was generated through a superradiance process, i.e. it extracted the energy from the black hole, then we know that, dE by dJ is omega r over m, or equivalently, we can just assume this is not a d, but just a delta. But delta E, basically the energy that is extracted from the black hole, is basically just the mass that is deposited in the cloud. Yeah, I mean, okay, so this shouldn't be a straight line. I'm not a good painter, I guess. But it's a curved line. Maybe that's the question. Okay, so then we know that the angular momentum in the cloud is just related to the mass in the cloud by this relationship, okay? And so with that, we can then rewrite this as the final angular momentum of the black hole is the initial angular momentum of the black hole minus this. So now what we try to figure out is where does the growth stop, okay? So basically, as the horizon frequency reduces while the superradiance cloud extracts the angular momentum, this line shifts over here, and eventually it will match up with where we sit in the parameter space, okay? So basically, what will happen is that over time, the superradiance condition will then eventually be satisfied at the location that we are at in the parameter space, okay? So what this corresponds to is that the horizon frequency is a function of black hole mass and black hole angular momentum in general. And now the assumption is that the horizon frequency of the black hole of the final mass and the final angular momentum is exactly equal to omega r over m, okay? So basically we're assuming that the horizon frequency initially was some larger number, but then over time it reduced because the background's black hole parameter is reduced. And so in the final state, so when the mass of the black hole is in the final mass and the angular momentum is the final angular momentum, then it matches, it saturates the superradiance condition. Okay, so perhaps it's easier to see this way. So initially, let's say initially we are in a cloud state where omega is smaller than n omega h, okay? And now let me just add, multiply an m on both sides, okay? And let me say that omega r is roughly mu. So this is roughly equivalent to mu m smaller than omega h, okay? Well, this is just alpha. And so initially, this alpha satisfies this condition in such a way that, well, it is now superradiantly unstable. But over time, this omega h reduces because the mass and angular momentum of the background black hole reduces, okay? So then end state is basically that this matches. And the reason that it matches is because at this point, omega I goes to 0 whenever alpha is approximately equal to m over h. Okay? So as soon as the horizon frequency matches the alpha, the growth rate goes to 0. And basically the superradiance growth, the extraction of energy from the black hole stops. And so now we're trying to figure out where this happens. And it happens exactly at this condition, which is basically just rewriting this, okay? But here, of course, crucially, the horizon frequency is no longer the horizon frequency of the initial black hole that we started with, but now it's the horizon frequency of the final black hole that has lower mass and lower angular momentum. Okay? Is this clear to everyone? So it is an assumption because I kind of, without saying it, described how the system behaves nonlinearly. So we're trying to understand the dynamics of a system that is ultimately governed by the Einstein equations, which are a nonlinear set of PDEs. And the assumption here is that the evolution of the background spacetime goes through a sequence of stationary Kerr black holes, each with a reduced mass and a reduced angular momentum. But the assumption there is that nothing else matters, really. That indeed the system will go through a sequence of equilibrium solution if you want, but it doesn't necessarily have to do that. It will turn out that this is a good approximation, but it is not generally the case that that would happen. In fact, tomorrow in the tutorial, we'll see that this is not necessarily true if you include gravitational waves, which I guess are one quote-unquote nonlinear effect. Because intuitively you can understand that, because here we've neglected gravitational wave emission, correct? And so when the cloud now starts radiating energy, then, okay, it still extracts energy from the black hole, but it also radiates energy away to infinity. So as soon as these two fluxes balance, they will stop growing. But they will balance before this condition is satisfied. It is approximately true to a very good degree, but it's not exactly true because we're neglecting nonlinear effects. Okay. So here, background space-time goes through sequence of Kerr black holes. And by Kerr black holes, I mean technically Kerr black holes, because if you then have gravitational radiation on top of that, it's no longer technically a Kerr black hole. Okay. So now, to understand how this saturation happens, and in particular, what the final mass and the final spin of the black hole are, we need to solve this equation, basically. Okay? And so, well, we already know the expression for omega h. I've written it down several times today. And it is a somewhat complicated expression that depends on the mass and the angular momentum. So I'm going to spare you actually solving this equation explicitly, but you can find a solution. And the solution is, right, I did miss something. So let me write this out again. But what you want to do is, you want to use these two expressions, right? Because we're trying to figure out what the cloud mass mc is. And so plugging those two expressions into the horizon frequency, we basically get initial mass of the black hole minus the cloud, and then the initial angular momentum of the black hole minus m over omega r times the cloud mass. And this we're now imposing to be omega r over m. Okay? And so this equation we can then solve for mc, and we get mc is equal to the initial black hole mass. Let me write it out first, and then we can discuss. Okay. So basically all I did was solve this for the cloud mass MC, and then defining this, as well as chi I is the initial dimensionless angular momentum. Okay. So now what we were able to do is we started out with some, linear solution to the Klein-Gordon equation that started extracting energy from the black hole. And by understanding exactly how this energy and the angular momentum are extracted, we were then able to write down a ratio between the two. And then assuming that the superradiance rate would go to 0 whenever the horizon frequency matches the alpha, we are then able to write down an expression for basically the final mass and the final angular momentum of the black hole, which we then can rewrite in just assuming that all the energy that was lost to the superradiance process is now deposited in the mass and angular momentum of the cloud. We can then rewrite the angular momentum of the cloud as just a function of the mass of the cloud using the expression we derived over there. And so ultimately, we then get a single equation for our single variable, the mass of the cloud, and we can actually solve it analytically. Okay. So now we know across the parameter space, meaning for different omega r's, for different m's, different spins, we know what the mass of the cloud will be as a function of the initial mass of the black hole. Okay. Okay. So as before, let's look at the behavior of this in the small alpha limit first, to kind of get an intuition for this large formula. Okay, and I'm going to spare you the details because, yeah, it's just a matter of algebra to actually do the expansion of this for small alpha. But basically, you just, omega r is basically mu plus alpha higher alpha corrections. And so this omega tilde will just be alpha. And then you just, expand this whole expression in alpha. And then you get the following. Let me write it here. So the cloud mass divided by the initial black hole's mass is equal to the initial spin of the black hole times alpha over m plus alpha squared corrections. Okay? And equivalently, using this formula, we can also get the angular momentum in the cloud, or conversely, it will be more interesting to see what the final spin of the black hole is. So the final spin of the black hole, chi f, defined as the final angular momentum, divided by the initial mass squared, is approximately equal to 4 alpha over m plus alpha squared corrections. Okay? Okay. So what we're learning here is that for small alpha, the total energy we are extracting, or we can extract in the deposit in the cloud, is very small because it scales with alpha. So for alpha to a very small number, this will also be equally a small number. Then of course it also scales with the initial spin, because the larger the initial spin, there's more energy to be extracted, and so more energy available, and so the mass of the cloud will also be larger. Okay? But then this is a bit funny here. So the final spin of the black hole also scales linearly in alpha. And so basically what this means is that even though basically you're extracting a very, very small amount of energy from the black hole, the final spin of the black hole is also 0, or approximately 0. And so all the angular momentum is actually deposited in the cloud, while the cloud itself only contains a small amount of energy. Okay? And so to understand the full picture, let me plot basically this expression as a function of alpha. And let me do so for a nearly extremal black hole. Okay? And again, as before, this is kind of just the most extreme case, and all the other cases look qualitatively similar. Okay, so for alpha roughly 1/2, and then this is 1, and this is 0. Okay. Okay, so we know the ratio, so the mass of the cloud compared to the initial mass of the black hole is very small for small alpha. And so conversely, we also know that the final mass of the black hole must be roughly equal to the initial mass of the black hole for small alpha. Okay, so if I plot here the ratio of the final mass to the initial mass of the black hole, then it will start at 1 and then decrease roughly linearly in alpha, depending on the spin. Okay. And then the final spin of the black hole will roughly increase linearly in alpha, like so. Okay, and so if we now look at the complete solution instead of just the approximation in the small alpha regime and plot this, what we'll see is the following behavior. So basically what this means is that for some intermediate alpha, so not the most extreme alpha where the superradiance condition is saturated, and not the smallest alpha where the cloud mass is very small. For some intermediate alpha, the cloud mass, the final mass over the initial mass of the black hole is smallest, and conversely, the mass of the cloud is largest. And so this roughly happens at 0.9. And so basically, what this means is that in the most favorite case, the energy of the cloud can be up to 0.1, and therefore 10% of the initial mass of the black hole. So what this also means is that of the available, in principle, 29% rotational energy that the black hole, in principle, possesses, we can only extract through this process roughly 10%. So only a third of the energy that we could, in principle, extract, we are actually extracting. And what happens to the rest of the energy? Where is that going? Well, number one, the final black hole is still spinning, okay? We only assumed that the saturation condition is satisfied. It doesn't mean necessarily that the final black hole is not spinning anymore. And so basically the final spin is some non-vanishing value. Okay, so there's still rotational energy contained in the cloud. But on top of that, we also didn't make any assumptions about the fact that the irreducible mass might increase during this process. Okay, so those two facts combined will just tell you that, okay, in principle, we could extract 29%, but in practice, we're only extracting up to 10%. Okay, and so in this intermediate regime, we're extracting some amount of the angular momentum of the black hole, but the remnant black hole, or the black hole once the superradiance condition is satisfied, will still be spinning. And in the most extreme case, so if we are basically starting at the saturation condition, then there won't be any unstable process, and so we won't extract any angular momentum to start with, and therefore the final spin of the black hole is roughly the initial spin of the black hole. Okay? So, as already pointed out, what we have neglected here is the gravitational radiation. And the place that will come in is basically by considering, as I already mentioned, kind of a flux balance law. Okay, so we have some energy that goes into the cloud. And then because the cloud is oscillating and radiating gravitational waves, some of that energy will get dissipated through gravitational waves to infinity. So on the one hand, the cloud is gaining energy from the black hole. But on the other hand, it's also losing energy to gravitational radiation. Okay? And so taking this into consideration, the final state of the black hole will not exactly be where this is satisfied exactly, but only approximately, because then you expect that it saturates or the growth stops when the energy extraction from the black hole exactly matches the emission of energy to gravitational waves. Okay? So how do we incorporate gravitational waves into this picture? Okay, so on Monday, I introduced this perturbative expansion around the Kerr black hole that we are ultimately interested in, right? So I assumed that the space-time could be described at 0th order by the Kerr space-time. And then at 1st order, we have some linear metric perturbations. And then I ignored everything at 2nd order. But let's now include the 2nd order. And ignore everything at 3rd order. Okay, so here the superscripts 1 and 2 just mean the linear perturbation and the quadratic perturbation. And equivalently, I wrote down the expansion for the scalar field, which at 0th order is, again, just 0. At 1st order, it is what we ultimately solved for. So that is, quote unquote, the hydrogen atom, the gravitational atom, the field configuration that extracts the energy from the black hole. And at 2nd order, it is something different. Okay? Okay, and as we already saw, the evolution equation for the linear metric perturbation, the leading correction to the Kerr metric, we found to be basically just the following equation. Under some gauge assumptions. Okay, and so what we concluded from this was that this is just kind of the evolution equation describing linear gravitational perturbation propagating on a Kerr background. And so basically, all the solutions of this equation will decay in time. So these contain the quasi-normal mode perturbations of Kerr black holes. It will include the late time tails of the decay of perturbations around the Kerr black hole. But everything is decaying here. And so then we said, okay, well, if we had a binary black hole merger, let's say, and then that formed a final remnant that would then approximately be Kerr plus some perturbations, these perturbations would die down long before any of the superradiance process would be important, okay? Or similarly, if you had, let's say, a black hole with some accretion disk around it, the accretion disk would only perturb the black hole very, 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 very slightly. And these perturbations wouldn't impact the evolution equation for the scalar field that we're interested in, okay? So this is epsilon to the 1. And so basically from this we concluded that we can just set, maybe I should add the indices here. We can set the linear metric perturbations to be 0. But at the same time, we then, of course, solved the linear perturbations to the scalar field are what we're actually interested in, right? Because those are actually the superradiant states that extract energy from the black hole. So this led to phi being, let me write it as phi superradiance. Okay, whereby I mean just all the superradiant states that we have classified by the different. Okay, so what we can then do is we can then plug this in here, and we can basically just replace this with our superradiant state, linear perturbations. And the linear metric perturbations we can just erase because they're 0. And so then the question is, how do we get the second order, like the H2s, epsilon squared? So let's first deal with the scalar fields. So in the case of the scalar field, ultimately the equation that we're trying to expand is the Klein-Gordon equation, which is a linear equation. So just so it all will make sense, let me write it out again. So the Klein-Gordon equation to any order is G alpha beta phi mu squared phi. And so if we're then trying to expand this to second order in these equations, then you'll see that, okay, this contains, okay, instead of looking at the Klein-Gordon equation, let's forget that for now. And I'll get back to you exactly how this looks like. But ultimately, it's not important, and I can tell you why it's not important by looking at the equations for the metric perturbation, which we're actually interested in. We're not really interested in any of this. So the metric perturbations, so again, the way to do this would be to take the Einstein equations and plug this metric ansatz into the Einstein equations, and then expand to linear order in the quadratic perturbations, okay? And then you'll get some second order PDE for those quadratic perturbations, okay? So schematically, this will look something like this. So now this D is no longer the D from over there, but now it's a second order differential operator. And this will be equal to T alpha beta. And not just any T alpha beta, but the T alpha beta that depends on our superradiant states. Okay? And so the reason that is true is because T alpha beta is quadratic in the scalar fields. And therefore the square of our linear perturbations, which are epsilon squared, of order epsilon squared, will enter in the source for our epsilon squared metric perturbations. Okay? So basically this is order epsilon squared, and this is, by construction, order epsilon squared. Okay? But now it also becomes clear why the linear metric perturbations didn't receive any source. Because the linear metric perturbations would be only sourced by some stress energy tensor, but the stress energy tensor is, by construction, quadratic in the fields. And therefore, the square of any linear perturbation would be higher order, which is why this is 0. Okay? But now add second order in epsilon, this is no longer the case. And now the presence of the superradiance cloud, meaning the presence of the linear solution, then sources metric perturbations at epsilon squared. Okay? So that's where our gravitational waves are going to come from. So the plan for tomorrow is to basically find a very neat way to solve this equation to then get the gravitational radiation. Basically because of the fact that the evolution equation for the linear metric perturbations is unsourced, and all solutions to this are decaying in time. Okay, so even if you perturbed the Kerr black hole somehow, the perturbation would just decay over time. But of course, this is no longer the case at second order, because then we have a source term which will keep driving the perturbations. Are there any further questions? That's right. Yeah, wow. So the quasi-normal mode timescales are much quicker than the superradiance timescale. Basically, because at the linear order, the metric will just be Kerr. It's Kerr plus 0 plus second order effects. And Kerr doesn't contain any gravitational waves. So to get the gravitational waves, we need to go to second order.
It might happen that because this is sourcing right now, then at the other order, it will source more. So this like exponentially goes, and these gravitational waves, like, but these are two separate cases where they will exponentially grow, or where we just stop at this order. And we are just looking at gravitational waves sourced by only this single phi.
Right. So that's a good point, yes. So in principle, there is, of course, an infinite tower of these equations, which will contain more and more higher order nonlinearities. And in principle, all of these are important. But it actually turns out that they're not really that important because the system goes through this sequence of Kerr black holes. So basically, the background spacetime is sufficiently close to Kerr all the time that we can consider just linear perturbations on the Kerr background. So nonlinear effects are basically highly suppressed beyond the gravitational radiation.
Okay, and also like the gravitational waves, these which are generated here, they don't perturb the black hole back, right? Or these are metric perturbations, and there are, by construction, then also perturbations to the 0th order, which are perturbations on the black hole spacetime. So, quote unquote, if we find the solution to this, then this is the perturbation on the black hole. It just so happens that that perturbation is also radiating to infinity. And we're mostly interested in that radiation to infinity, as opposed to the radiation or the perturbations close to the black hole. Okay, because I was thinking in terms of like, it doesn't ring down, but it rings up, you know, like because it.
Right. Yeah, that's true, because the source term will grow exponentially. The quote unquote ringing, which is the gravitational waves or the gravitational perturbations, will also grow exponentially in time. But then at some point, this exponential growth, of course, stops. And then the cloud just sits there, and then the ringing is just kind of constant in time and will decay over a certain time scale.
Okay. Then let's thank Nils for the lecture.